I'm not sure why I was muted. Hey guys, so linear family of functions. Obviously, the name itself is telling you we're talking about straight lines here, all the linear functions. So with linear functions, you know, our transformations are going to look a little bit different than they did for, let's say, a square root or a square function. So here they're telling us, of course, our base function is going to be the identity function, which is our y equals x function, because remember, this is where when I set my tables, I always get y equals x. So if my x values are -2, -1, 0, 1, and 2, my y values will be the same, right? They're going to be identical. So that's what actually gives it the name, the identity function. We know this is a graph that passes through the origin at 0, 0 and has a slope of 1. So what will a transformation on a linear function look like? It actually ends up giving you an equation. Even if you start out in this form, your final equation is going to end up looking like the slope-intercept form, because you just end up with whatever the slope of your line is going to be and the y-intercept. So just to kind of show you how that transformation happens, we're starting out with our transformation equation. So remember, a is the value that gives us either the stretch or the shrink, and then if you put a negative on that a, it gives you the reflection. The h gives us the horizontal translation, and the k gives us the vertical translation. So the idea is, if we start out by distributing that a inside the parentheses, you end up with a times x minus a times h, and then just bringing that plus k down. Now, x, of course, is my variable term, but the numbers a, h, and k are all going to be real numbers. So I can actually go ahead and combine these terms and simplify them, which will end up becoming our b value, the y-intercept. I can replace that a with the letter m, my slope formula, and you basically went from the transformation form into the slope-intercept form. So anytime you look at equations for a linear family of functions, they are all going to end up looking like this, because once you clean them up, there's really nothing else left for us to show the transformation happening. So, you know, obviously, they're asking us to use transformations to graph this function. So we'll do kind of what we had done in the previous example and break this down into individual steps and see how that transformation happens. So start out with your table. And, you know, we should be able to use, hopefully, our standard 5 points and still get some good numbers out of this. So let's do -2, -1, 0, 1, and 2, right? But remember, we're doing this in steps. We're doing this as transformation. So all base functions are going to be your y equals x, or the identity function we looked at the top. Now, do you remember the order in which we do multiple transformations? So just if you go back to the previous page, we do horizontal translation first, right? Then we do reflection, stretching, or shrinking, depending on what you have. And then the last thing we did was vertical translation. So let's see which ones of these apply to our linear function here. So remember how our values all combine here to form the b? So you're really not going to have a separate horizontal movement here. So basically we have a reflection from the negative. 2 tells us, is it going to stretch or shrink? It's going to stretch. If the value is greater than 1, your function stretches, and the +5 will actually represent the vertical movement. So that's going to be our transformation. We start with the base function, then we move on to, we can do the reflection next, okay? Then we can do the stretching, and then the very last thing we'll do is the vertical movement. So I'll actually create a table for it down here. So we're starting out with the original base function. So what will my y values be here?
is just going to be the same number as the x's.
Yeah, because obviously remember these are the identity functions, so they will be identical. Okay, so I'm actually going to do my graph right here. So what was this, number 9? So starting with our y equals x function. Then we were looking at reflection next. So with reflection, how do things change for the y values? Yeah, your signs on the y values will change because now you will have -2 from the x value and then that extra negative sign in there. So the two negatives become positive, of course, keeping our x values the same. So this will become now +2, +1, 0 of course doesn't take a sign. And then the +1 will now become -1, +2 becomes -2. So all the y values from my original function will now change signs in the reflection. So when we try to graph it, and we had actually seen an example like this when we did reflection, you are still at 0, 0, but now +1 is -1, +2 is -2, and then of course positives on this side. So this will be our reflection. Now, for the stretching, what change do we make from this table to this table, where you have y equals -2x? We're still keeping the same x values.
Just multiply that by 2.
Yeah, just multiply all the values we have here in our second table, multiply all of them by 2, and you're going to get the result for this one here. So what will that end up being?
4,
2,
0, -2,
-2,
-4.
There we go, -2, -4. So 4, 2, 0, -2, -4. A little off, but basically what happened is the line that was in red, which was our line of reflection, will now become a little bit steeper when we multiply by 2. So your slope, of course, increases, increasing the steepness of our graph. Okay, so that's almost to the end. Now all we have to do is complete the final stage, which is moving our graph 5 units up. So what kind of change do we need to make to get this last table here? Again, we're still keeping the same x values.
We're just going to add 5 to every y value.
Yeah, just from the table of -2x, which is this last one here, you're just adding 5 to all the y values to get the table completed. So what will it be for this guy here?
9, 7, 5, 3, 1.
Okay, so 9, 7, 5. You said 3 and 1?
Yeah.
Okay. Okay, so what will that graph end up looking like? Looks like I don't have a 9 or a 7. 1, 2, 3, 4, 5, 6, 7. So 7, 5, 3, 1. Okay. So if you look at the line that we did last, which was the line in green, and again, I'm just using my point at 0, 0. If I use that, 1, 2, 3, 4, 5, obviously you should see that line has moved up by 5 units. So we still have a negative slope. It's a steeper line because of that -2, and the +5, of course, for our vertical translation. So just to show you that on our graphing calculator, we started out with X, we did a reflection on that, right? Then we multiplied it by 2, so that gave us our stretch, and the very last part was adding that 5. So obviously between our last 2 lines, you should notice these lines are going to be parallel. So as you draw them, be careful about these 2 lines here. They need to be parallel to each other because they have the same slope at this point, right? Just different y-intercepts. And if we get rid of all the intermediate steps, then this is what our final function should look like. What do you think will be, not you, the domain and range for our final function?
Would it be -infinity to +infinity for both of them?
For both of them, yeah, because obviously this is a straight line. It is still going to go in both directions. So as far as our domain and range goes, this arm is still going up to +infinity on the y-axis, and on the left, it's going to -infinity. And then this arm of our graph, of course, is going down to -infinity on the y-axis, but then to the right to +infinity for x. So in this case, from the original function y equals x to this one, your domain and range will stay the same for both functions. And like we saw in other examples, that's always how straight lines work out to be. So just so that you guys are aware of this on your exam, if you see a graphing equation for a straight line, just use your slope and y-intercept to graph it, right? Don't worry about transformations in that case. But if you do see an example like we did last time with this one, and they're asking you to use transformations, and remember what I told you, show me the tables of the transformation happening, but then the graph, you are just graphing the final function, because you really won't be able to graph all of them and make it look neat just because those graphs are so tiny. So just remember that for that other function. All right, anybody have questions on this guy?
So you're saying on the test we only did the last step?
For the graphing part.
Mm-hmm. Well, the first and the
But
last.
For the transformation, I want to see the table.
Right, but if it just asks you to graph the linear function, is what
That's just the line then. Yeah, then you don't even have to worry about the table in that case. Yeah, so it's only for the anything that's not a line, basically. Because I'm just assuming you guys know how to draw lines at this point. So I'm not having you do all that extra work with lines. But for the others, I do want to see a transformation. And like I said, not on the graph, but at least a table to show me the different stages of transformation. So this next part we're getting into is symmetry, as you can see. So of course we know that if we graph our reflection of the original function, so we're looking at x squared, and its reflection negative x squared. So of course x squared will be the graph here in red, negative x squared is the one here in yellow. So if we talk about symmetry, the idea is if I were to fold my graph along the x-axis, right, the two halves would coincide. So the curves would match each other exactly. If you talk in terms of distances, then think about the distance from the x-axis. So if I use this point, -2, +4, and -2, -4 on the other side, then the distance from the x-axis to this point and the distance from the x-axis to the one underneath that is going to be the same, right? Those two distances are going to be exactly the same. So we can say there's symmetry on these graphs in terms of the x-axis because that's where the symmetry is happening. But now parabolas actually bring their own symmetry. So the idea is something similar here. If I fold along my y-axis, so if I fold the parabola along the y-axis, then those two halves will also coincide. So in terms of distances, again, if we're looking at points 1, 1 and -1, 1, we know this distance from the y-axis is going to be same going on either direction. You can select a different point on your parabola, and again, the distance from the y-axis from one side to the other side is going to be the same. So when we're actually talking about symmetry, we're talking more about symmetry like this with the y-axis and not so much with symmetry on the x-axis. Because the main reason of not using symmetry on the x-axis is because if you have functions that have symmetry with respect to x-axis, they're actually not going to be functions, right? Because they fail the vertical line test. Think about a parabola that opens on the right-hand side, right? When I draw a vertical line through that, it's going to fail being a function. So it's an equation, but not a function. So that's why we're not looking at symmetry with x-axis. We're looking at symmetry with y-axis, and we'll also look at symmetry with the origin. So when you're talking about symmetry with the origin, we're actually looking at the x cubed function. So in this case, we really won't be able to like fold our graph and make them coincide like a parabola does. But with functions that are symmetric about the origin, you can still use the idea of that distance. So if I'm comparing the points +2, +8, and -2, -8, and I take the distance from the origin, from 0, 0, then this distance on the upper half is going to be same as the distance on the lower half. So a function like x to the third power, we will actually say it is symmetric about the origin. So it's symmetric about a point. But a function like x squared, our parabola, is symmetric about the y-axis itself. So functions that have symmetry about the y-axis are what we call as even functions. And I'll talk about this here in a minute, but we're basically saying if you substitute your x with a negative x, you should still end up getting the original function. And this only happens if your function is an even function, okay? With odd functions, something like x to the third, they will have symmetry about the origin, so they're going to be odd functions. And odd functions, the idea is if I replace my x with a negative x, I actually end up getting the function, but with a negative sign in front of it. So basically we're saying it makes the entire function a negative function. So those would be the two ways that we can tell, are we looking at an even function or an odd function in that case. Now they're telling us that a graph may look symmetric about the y-axis or the origin, but graphs can be pretty deceiving, so we don't really just visually depend on what kind of function we have. We of course want to make sure we test it algebraically and make sure we are getting an odd or an even function. So let's start out with what happens when we take, I don't know, a number like -3, and let's raise it to the third power, and let's raise it to the fourth power. What are we going to get? -27 for the first one, -3 times -3 times -3, right? So 3 times 3 is 9, 9 times 3 is 27, so we know the 27 works out. But then you also have 3 negative signs coming from each of these numbers. So we know two negatives will become positive, but that still leaves us with the negative sign behind. So that's where that negative is coming. What will -3 to the 4th power give us?
81.
Positive, negative?
Positive.
Positive. Because basically you're just taking -27 and multiplying it by one more -3. So that means the two negatives will become positive, and of course 27 times 3 gives you 81. Now does that work with any number other than -3? So what if I change this to, I don't know, let's keep it small, -2 and -2. So -2 to the 3rd power, will I still get a negative answer? Yeah, what do I get? -8 and -2 to the 4th power.
16.
Positive 16, right? So this is actually not really dependent on what number is on your base. It's that negative sign that makes a big difference. So the idea is, if you have a negative base, but your exponent is even or odd, is where the difference actually happens. So anytime you have a negative base with an even number, and this is of course going to be true for your exponent being 2nd power, 4th power, 6th power, 10th power, doesn't matter. You are always going to end up getting a positive result, right? But if you have a negative base with an odd exponent, so if my exponent is an odd number, you will actually always have a negative sign left behind. So this little description that I have here, that's what it's talking about. So if you have a negative base with an odd exponent, you are going to get a negative answer left behind. If you have a negative base with an even exponent, your answer is going to become positive. And this part is really crucial when we're trying to decide, are we going to have an odd function or an even function? Because, you know, once we put our negatives in, we need to see what comes out of that. So let's start with this example here. They're saying determine algebraically whether the function is even, odd, or neither, and then based on what type of function they are, we can of course talk about their symmetry. So let's go ahead and see what we need to do here for this example. We've got f of x equals x to the 4th minus x to the 3rd. And to test this algebraically, we basically start out by taking our function and replacing the x with the negative x. And then we're trying to see, do we come back to the original function? If we do come back to the original function, that means it's an even function. It has symmetry about the y-axis. If we come back to the negative of the original function, then that means we have an odd function and it has symmetry about the origin. So that's basically what we're trying to see. And of course, your third option is it's neither. Okay? So everywhere that you have an x, you replace it with negative x. Okay? So everywhere that we had an x, we replace it with negative x. So that means you end up getting negative x to the 4th power minus negative x to the 3rd power. So kind of like how I was showing you here, that's why we needed to know what happens when I have a negative base with an even exponent or a negative base with an odd exponent. So what will happen to my negative x to the 4th power? Will it stay negative? Will it become positive? Stays negative? When it's an even exponent?
That's positive.
It's positive, right? Because that's to the 4th power, which means negative times negative will become positive, and then the other two, negative times negative, will become positive. So this guy will end up becoming positive x to the 4th, because that's what that even exponent of 4 will do. If you need to write it out, go ahead and expand that. So you're looking at negative x multiplied into itself 4 times, right? Which will become positive. Now, what will happen with the negative x to the third power? It will stay negative, yeah. So you will actually end up getting negative x out of the 3. And then I still have this minus sign from the problem itself. So the two negatives will actually end up becoming positive. Now, is this the same function that I started out with? No. So this is not equal to the original f of x function, which means this is not an even function. And if it's not an even function, which means it does not have symmetry with respect to the y-axis. Now, how do we know if we have an odd function? So for an odd function, the idea is you take your original function f of x and put a negative sign. Put a negative sign in front of it. So if I distribute that negative sign into my original function, what do I end up getting? Negative x to the 4th
Plus x third.
positive x to the 4th. So is this what I had when I did this little math here? Did I get negative of the original function? No, because the only difference is I don't have a minus sign here either, do I? So that means this function is also not equal to the negative of the original function. So it's not even, and we just proved that it's not an odd function either. So let me kind of go through this one more time. This is the function we were given. They're asking us to determine if it's an even function. Even function means it has symmetry with respect to the y-axis. If not, is it an odd function? Because an odd function would be symmetry with respect to the origin. So the way you test it is start by taking the original function, replacing your x with negative x. So we ended up getting negative x inside the parentheses raised to the 4th power, minus, again, negative x in parentheses raised to the 3rd power. When we simplified it, our function ended up being x to the 4th plus x to the 3rd. It definitely does not match the original function we started out with. So that tells me it's not an even function. It does not have symmetry with respect to the y-axis. To check and see if it's an odd function, you take your original function that you started out with and literally just put a negative sign in front of the function. In this case, I distribute my negative and I end up getting negative x to the 4th, positive x to the 3rd. And again, that's not the same thing that I got when I put the negative x in this part. So since these guys don't match, that means I don't have an odd function either. So since I don't have an even function, I don't have an odd function, our conclusion should be this is neither. And since it's neither, we can say there is no symmetry. Well, let me show you what that original function actually looks like. So this is x to the 4th minus x to the 3rd. X to the 4th. This side will be x to the 3rd. And look at how that function looks, right? So even if I were to fold it along the y-axis, my two halves would not coincide. So there's no symmetry with terms of the y-axis. If I was to take the distance from the origin, even if I randomly picked this point here and this point here, they're not going to be the same distance from the origin. So with respect to both our symmetries that we've talked about, this guy has neither. Even if you zoom out for quite a few movements, you can see it's still not symmetric, but this is what happens if you zoom out far enough. it may actually just look like it's a parabola shape, and you may think it has symmetry. So that's why we don't really just depend on visually checking and seeing if the functions are symmetric or not, because obviously the moment I zoom in, I can see this guy really has no symmetry at all. Any questions on number 10? Okay, so do we see how to check algebraically and how to do this? Right, let's try it here with number 11 now. And so remember, you start out by replacing your x with negative x. So basically that ends up giving f of negative x equals negative x in this case, right? I definitely don't have my original function. So since I don't have my original function, it's not the same as f of x, which means this is not an even function. If I wanted to check and see, do I have an odd function, take your original function and put a negative in front of it. Now, do I have a negative of the original function? I do, yeah, because obviously you can see both of these are negative x and negative x, so that tells me this function here is equal to the negative of the original functions, which means I have an odd function, and odd functions have symmetry about the origin. The best way to remember is odd function begins with an O, origin begins with an O. So if you can claim that it's an odd function, then the symmetry is going to be with the origin. If it's even, remember, even is the one that goes with the y-axis. If you can remember that O goes with O, then it'll really help you remember and keep track of your symmetry. Because the one greatest mistake I see happening on these questions on the exam is I'll ask you to check and see, is it an odd function, is it an even function, and then talk about symmetry based on that. And a lot of times you will have the correct function, so you will say, yes, it's an odd function, but then you don't remember, oh, well, does the odd go with the y-axis or the origin, and you'll end up choosing the wrong symmetry. Or sometimes you know it should be symmetric about the y-axis, but then you end up choosing it as the other function. So a lot of times we're having that disconnect between what function goes with what symmetry. So if it helps, think about O goes with O, which automatically means the other two options have to be together, which is even and y-axis. Okay, so this is the function that we just looked at when we did our linear family, but if you think about the graph for this, it's your simple y equals x. And think about it, it does have symmetry about the origin, because if I pick a point, let's say +1, +1, and -1, -1, they are going to be the same distance from the origin. So I know this graph has symmetry about the origin, and we just proved that algebraically. What do you think happens on number 12? Okay, so we are given f of x equals absolute value of x squared minus 3. So to start with our testing, replace the x with negative x. So when I have a negative exponent, a negative base with an even exponent, what happens to my signs? it becomes positive. So we end up getting positive x squared, and then of course keeping everything as it is. So do I have the original function that I started out with? I do, yeah, because obviously you can see I came back to the same thing, which means this guy is equal to the original function, and if he's equal to the original function, then that means it's an even function, and even functions have symmetry about what?
Y.
Yeah, about the y-axis, so that's symmetric. About the y-axis, and just to show you the graph for this guy really quickly. Of course, we know it's an absolute value function, which means we should have at least part of that V shape, if not all of it. So we're doing absolute value of x squared minus 3. And obviously, you can see as far as symmetry with the y-axis goes, we can actually fold along the y-axis, and our two halves will coincide. So this one definitely proves that it's an even function. Okay, so symmetry about the y-axis for number 12.
So once you find that it's an even one, you don't have to check that it's odd, because you know, I mean.
Yeah,
Yeah, there's
because
no
it's got to
reason
be
to
one
go.
or the other. It couldn't be obviously both.
Right.
Yeah, very good. Any other questions on that? Okay. What do you think happens on number 13? Complicated? Why?
The last one's always complicated.
The last one's always complicated. Do not listen to him, people. So, Trey, do you have a conclusion on what you think it should be? Should it be odd? Should it be even?
I think it's gonna be, actually I do, I think it's gonna be odd.
You think it's going to be odd? So obviously we take our function and replace it with the x with negative x. So this guy would end up becoming what? Negative x plus 3 squared. So what does that tell us? Do we have the original function? Definitely not the original function. Do we have a negative of the original function? Yeah? No? Jose, you're changing your answer on me? You are? Okay. So in this case, it might actually help to go ahead and FOIL the original function just to see what's happening. So if I go ahead and FOIL this original function, what do I end up getting? Yeah.
X squared plus 6x plus 9.
Yeah. Alrighty. X squared plus 6x plus 9. So now think about what happens if I put my negatives in for these x's. You will have negative x squared plus 6 times negative x plus 9. If we clean that up, what do we get?
Squared minus 6x plus 3.
Yeah, so the negative x squared to the second power will of course become positive. Positive 6 times negative x will become negative 6x plus 9. So we kind of knew that from here, but you can see we definitely did not come back to the original equation that we started out with. So we know this guy is not equal to the original, which means we don't have an even function, right? Now to check and see if we have odd, you take your original function and just put a negative in front of it. So either in this form or either in the FOIL form. So So if I put a negative in front of the original function, what will this guy simplify into? Yep, negative x squared minus 6x minus 9. So did I have this here in my checking? No, because I'm missing a negative sign on the x squared and the 9, right? So they're definitely not the same terms, which means this is not the negative of the original function either, so not an odd function. So does that mean it has no symmetry then? Isn't that what we did for the first example? We said no symmetry?
Mm-hmm.
Let's see what the graph for this guy says. So you can write the other version also, but I'm just keeping it to the original. So what are we noticing here? Kind of. It's a parabola, right? Parabolas have their own symmetry. So yes, it is not symmetric with respect to the y-axis because obviously it's nowhere near the y-axis as far as the symmetry goes, and it's not symmetric with respect to the origin. So if you're only checking for symmetry with y-axis and origin, then yes, we will say there is no symmetry. But if they're just talking in terms of general symmetry, then we will actually say that this function is symmetric about the line x equals -3, which is actually coming from that x plus 3 in the original format. Let's go back to the graph. So if you see with my -3 here, that's where my line of symmetry is going to be. So if I fold my graph along this vertical line x equals -3, my two halves will coincide. So with respect to it not being an even function, we know there's no symmetry in terms of the y-axis. Not being an odd function, we know there's no symmetry in terms of the origin. But because it's a parabola, it's bringing its own symmetry. Okay, so just something to think about while you're working through these.
So how do we know that with looking at the problem or without looking at the graph? How would we know that?
So you would actually look at how the question is stated. If they specifically, especially because these questions are, I think, my math lab mainly gives you multiple choice on this, I believe. So they will either give you the option of typing in your symmetry, and if they're giving you the option of typing in your symmetry, that means they'll accept this answer. If they give you like radio buttons where it says symmetry about the y-axis, symmetry about the origin, neither. Then you know they're not asking you for the third option. They're just saying if it's neither, then you go with neither, right? Then you don't have to say it's symmetric about x equals -3. So it's really about, are they asking you to type in the equation, or they're asking you to choose between those three options, when neither is one of them. So you really have to see what format the question is in.
But I mean, like, how would we know that? Like, if we saw something like this on a test or anything without looking at
That's
the graph?
what it would look like.
Would it show us the graph though? That's what you're asking.
I don't think
Without
it would
looking at
have
the
the
graph, how would you
And I
know?
mean, just like if we don't have a graph and like
But
it's
you know,
like
I
it's
mean,
not even
it's
or
not
odd,
going to
like,
take
how
you
do
that long to draw a graph if you needed the graph to support you, which you shouldn't need the graph because this is a second-degree polynomial. Remember, we talked about this in chapter 1. All second-degree polynomials are quadratic equations, right? Quadratic equations, all their graphs are parabolas. So that's what I would use, is the idea that this is the second degree, or the square is my highest degree on this polynomial, so it's got to be a parabola. And all parabolas bring their own symmetry. So if they are at the y-axis, then of course they would end up being the even function. But if it's something like this, where it's a little bit to the left, then they're going to bring, or they could be to the right. It really doesn't matter. Parabolas keep moving apart. about. So you could have symmetry on the negative side of the x-axis, you could have symmetry on the positive side. But like I said, if you needed to do a graph to kind of just make sure and confirm, then do a little scratch work on the side and see, you know, where the line of symmetry or actually the axis of symmetry would be. So you can do it that way. Does that answer your question or not?
Mhm.
Yeah? Okay. Anybody else have a question on this? Okay. So let's go back to our handout. Now this little guy here is actually talking about how easily you can identify what kind of a function you have in terms of is it odd or even, just by actually looking at your graph, the equations themselves. So they are saying that if you have a function where all the exponents are going to be even exponents or all the exponents are going to be odd exponents, then you actually know what kind of function you have. So just as an example, you can have something as basic as x squared, which is an even exponent, or you can have something like this, x to the 6th, that's an even number, x to the 4th, again that's even, x squared is even. Now this plus 3, it's kind of interesting because you can think about that as being 3 times x to the 0 exponent, and even though normally we don't think of 0 as being an odd or an even number, in this case we're actually assuming that 0 is an even number. So that means I have an even exponent here, even exponent here, even exponent here, and an even exponent on that plus 3, which means since all my exponents are even, this function is even. For an odd exponent, you can again have something like just x to the 3rd power, where that's an even exponent, or x to the 5th, x to the 3rd, x to the 1st, right? All odd numbers, which means this function here is actually an odd function, which means it will have symmetry about the origin. So if we go back and look at our examples here, this was a combination of odd and even powers, wasn't it? X to the 4th and x to the 3rd. So you can see it could not be classified as one or the other. It ended up being neither. And we looked at this graph and we know it had no symmetry of its own. This guy here is just x to the 1st power, right? That's an odd number. This guy was an odd function. It has symmetry about the origin. The next one here is even on the x squared. And remember, for constant terms, we said think of them having a 0 exponent. So that also became an even number. So we had symmetry about the y-axis. This was an even function. Now this guy here, when we actually FOIL it out, we ended up getting x squared, which is an even number, 6 to the x, x to the 1st power, that's an odd number, and then the 9, of course, if you think of that 0 exponent, is an even number. So we have a combination of odd and even. So obviously, as far as type of function goes, it was neither. And since it's a parabola, it brought its own symmetry to the game, but otherwise, it does not fall into these two categories of odd and even function. So you can actually just look at the exponents for the given function and decide if it's going to be an even function or an odd function. That can also help you determine what kind of symmetry you have. And I already kind of talked about why we're not using the x-axis symmetry, because then your graphs end up not being functions. They fail the vertical line test. All right, so this last part here is actually talking about how we can use graphs to solve inequalities. And we're starting out with looking at x minus 1 squared, quantity squared minus 9. So we actually want to start out by graphing that example first before we can start thinking about solving the inequality. So let's see how we can go about doing something like this. Okay, so this is what we are given. So the first thing we're going to do is actually take that first part and think of it as an equation of a function. So y equals, or you can write it as f of x, doesn't matter, x minus 1 squared minus 9. So we want to start out by graphing this guy first, and then we'll come back and see how to solve that inequality. So what kind of x values can we go for to try and graph this? And I think the graph for this is over on the other page. Yeah. What kind of values can we use for x and y? Okay,
Lower than -2.
say that one more time.
I said any number for x lower than -2.
Okay, and why are you making that cutoff at -2?
Because I know it can't be, like I know going back it can't be greater than 0, and then so -2 minus 1 is -3 squared is 9 minus 9 is 0. So
Okay.
I know that anything past -2 will give us an answer that we can
Not use?
use.
We can use.
So we can't use anything above -2.
We can't use anything above -2. Well, think about this. This is an x minus 1 quantity squared. So when I spread it out, it's going to be a second degree equation, right? Which means it's going to be a parabola. And in general, what is the domain of a parabola? Negative infinity to infinity, right? So technically, we do not actually have restrictions on our domain. Now, we may have happy numbers and not so happy numbers to use, but as far as just choosing anything, you can obviously go to a wide spectrum. So you said go lower than -2? So give me some numbers.
-2, -3, -4.
Okay. And let's, you want to do -5?
Sure.
Sure? Okay. I'm not sure what happens with -5. I've never tried a -5 on that. Okay, so let's see what kind of y values we're going to get. So remember, this is where you're putting in your x, right? So that's going to be -2 minus 1, which is -3, as you mentioned, -3 squared, positive 9, 9 minus 9 is going to give us 0. So what are we going to get for -3? Yeah, because you're going to get 16 in the parentheses part. So 16 minus 9, give us 7. -4, 16. Okay, so this may actually be going a little bit beyond what we can graph since we're doing a 10 by 10. So I'm actually going to take that -5 out of the game. What can we do then from the other side of -2?
0, 1, 2, 3.
Okay, I'm actually also going to use -1,
Oh, there you
just so I know what's the next thing happening here. 0, 1, 2, what else did you say?
3 and 4.
3 and 4. Okay, let's see if we can bring this guy a little bit down. So 3 and 4. Okay, so with -1, what will we get? -5, yeah, because you're going to get -2, which will become 4 when you square it. 4 minus 9 will give us -5 with a 0. Sorry?
-9.
-9? Nope.
Nope. -8.
-8. Okay, with a 1,
No, that was -9.
that would be -9. Alrighty, and then with the 2,
-8.
yeah, it looks like it, doesn't it? Number 3,
-5.
-5 again, and 4.
0.
That would be 4 minus 1, which is 3.
0.
0. Okay. And so we are going from -4 to +4 on the x-axis. how far are we going? 16, so we won't be able to do that, but we've got -9. Okay. I think my scale's a little off, but we should be able to work this out. So we've got -2, 0. -3 and 7. Somewhere about here. Okay, so I won't really be able to graph my -4 and 16, so I'm going to leave that one out. I've got -1 and -5. So right about here. 0 is at -8. So about there. 1 is at -9. 2 is back at -8. 3 is at -5. So your 5 should actually bring us back to 7. Just if you go with symmetry. Right? So that should give us a pretty decent idea of the shape of our parabola here. Something like that. So the additional point I added was 5 and 7. Now the idea is, how is this graph going to help us solve this inequality? So remember, we're setting all of this equal to y. So we are basically wanting to know on what interval, because remember, absolute values, not absolute values, inequalities always give you solutions as intervals. So they want to know on what interval is the y value going to be less than 0? On what interval is the y value, so for the graph that we just did, is going to be less than 0? And remember, this is not including 0. So look at your graph and see what part of my graph has negative y values. Spencer? Not sure?
I was gonna say at the origin.
At the origin, okay. Yeah, so at this 0, I do have a -8 there. To think about in terms of the axis itself, all of these numbers on the y-axis are negative numbers, yes? They want to know when is y going to be less than 0, which means when is y going to be negative. The y is negative for the graph when it starts from here. All of these points going from, what is this number? -2? That's moving a lot. What is this number? 4. So all the points that go from -2 on the x-axis to 4, aren't all of those having negative y values? Now at -2 and at 4 itself, what is my y value?
0.
It's 0, and you can use your table to verify that. Now once I cross -2 and 4, what happens to my y values on this side?
Or they just disappear. Or they just can't be in the equation.
It cannot be part of our answer, right? Because my y values are positive. So for this little section here, this little section, all your y values are going to be positive. This section here, and of course, these guys are going up to infinity, your y values are going to be positive. It's only from this section, which actually continues on the other side, is where our y values are less than 0, and of course, this section here where the y values are going to be less than 0. Right at -2. This is, of course, if I write it as an ordered pair, this is -2, 0. So my y value is actually 0 at that point. This point here is going to be 4 and 0. Again, my y value is equal to 0. We're not interested in where it's equal to. We want to know where it's less than, and that's going to be in the interval so going from -2, which is starting at this point, going all the way down, following my graph, till I get to 4. All my y values between those x values are going to be 0, or sorry, less than 0, and I am not including my endpoints. If they had given us less than equal to 0, I would have put brackets on my endpoints. But since they are saying specifically less than 0, we don't include our endpoints in there. The only other way to solve this would be solving that quadratic equation and figuring out where your x values are going to be less than, your y values are going to be less than 0. Right now, we're just trying to use graphs to help us solve this. So just as a recap, we started out by graphing our given equation. So that was x minus 1 squared minus 9. Once we graph our little equation here using our little table, then we were trying to decide where do those values end up becoming less than 0, and where they're going to be negative. So this portion of my graph falls on the negative side of the y-axis, so I know all of these y values, if I look at these ordered pairs, are going to be negative. Once I cross the x-axis and go above it, my y values start becoming positive, so I'm obviously not interested in that portion of my graph. If you take anything that goes between -4 and 0, put it in the x, you should get a negative answer for the y. And think about it, between -2 and 4 would be -1. When I put -1 in my function, I got a negative answer for my y. When I put 0, which is also between these numbers, I got a negative. 1, 2, 3. Look at all of them. They all gave me negative y
You said
values.
-4 and 0. Were you meaning -2 and 4?
-2 and 4. Right? So any number between those, not including the endpoints, is going to end up giving me a negative answer for my y values. So that is the range that I'm looking for, or actually the word would be the interval that I'm looking for. Okay? You have the same exact thing on the next example. They're just changing the function here. So start by graphing what 5 minus square root of x would look like. So create a table and see what that ends up looking like. So I can start by creating a table like we did for the previous example. Then graph your function. You could have also thought about this in terms of transformations, because this is given to us in the transformation form. The -9 told us our graph moved down by 9 units, and of course you can see we were down at -9 for the lowest point. The x minus 1 actually told us our graph moved 1 unit to the right, and you'll notice I'm not at the 0, 0. I'm at 1 unit to the right and 9 units down. If you use transformation for this example, your base function is the square root of x that's being reflected, and then what's the 5 telling us? Yeah, it's more going 5 units up, because that's actually, you can put it at the end and say +5. You know, if 5 is positive, that means the graph moved up. So imagine that when you're graphing your function, that's kind of what this graph should end up looking like. And then what kind of x values are you allowed to put inside a square root of x? And 0. So you can have 0 in there, and you can have positive numbers in there. Do you have your table? Yeah? Give me some numbers.
0, 1, 4, 9, 16, 25,
0, 1,
4,
4,
9,
9.
16,
Okay.
25.
We of course won't be able to graph the larger ones just because we're restricted by our grid. But yeah, you can use anything in there. So when you put a 0 in there, what do you get for your y value? 5. For the 1,
4,
4,
3,
3,
2, 1, 0.
but like I said, we really won't be able to use those points. So what does this graph end up looking like? We've got 0, 5, 1 and 4, a little off, 4 and 3, 9 and 2. And 9 will be somewhere over there. So 9 and 2, maybe somewhere over here. Right, we should have a function that looks something like that. So where is it crossing the x-axis at? 25. We're actually going to need that on our graph, because this guy is talking about specifically where your function is equal to 0 and greater than 0. So how can we modify this graph to accommodate showing where it's crossing the x-axis at?
Make the amount.
Shrink your values on the x-axis, so you can do that. If you've already drawn this, then I would say for now, go ahead and extend your, if you have space, I guess you do, just extend it out till you can get that mark for 25 on the right-hand side. So I'm gonna try and see if I can modify this one just a little bit. I don't know, this is really not to scale, but just to show you that it would, what it should look like. So if this is 5 on the y-axis, just make sure you cross at that 25, and then your graph starts going down. So show that curve crossing at this point, 25 and 0. More like that. So they want to know where are your y values going to be equal to and greater than 0? So what interval will that be? Because now we want our y values to be 0 or positive, right? Because we're saying greater than 0. So if I just look at this, give me the value for 36.
Gonna be negative 1.
So after we basically cross 25, we're starting going to look at negative y values, right? Because the moment I cross 25 on my x-axis, now my y values are going to start becoming negative as that arm goes down. So from here onwards, your y values are negative. On this upper half, which is, this portion of our graph, this is where your y values are positive, and then of course right at this point is where I have the x-intercept, which is 25, 0 coming from this point. Yes?
So the interval would be from 0 to 25 and including both 0 and 25, correct?
Yeah, right? Because at 0 itself is where I have my 5, right? So of course my y value is positive here. And then till I get to 25, they're all staying positive. At 25, it becomes 0. Since we are including 0 in there, obviously I can use 25 also. But you can do 25.00001, put that in a calculator, and you're going to start looking at negative y values at this point. Because, of course, square root of 25 gives me 5. 5 minus 5 is 0, and this is where all my positive numbers are going to stop. And I'm going to start heading into negative. So, yeah, that's your solution set. You will be going from 0 to 25, and that's on the x-axis. At 0, I have a positive value, and then at 25, I have my 0, and since we're including 0, you put bracket on 25. If you were not including 0, and this was just greater than, then it would have been bracket 0, 25, and then 25 would have had a parentheses on it. Okay? So because of that greater than equal to, the 25 also gets a bracket. So yeah, that's the idea of trying to use a graph to solve these inequalities, other than the traditional method that we looked at in chapter